Students, this is a lab called the molar mass of a gas. And the idea here is we're going to take a standard, what they used to call a cigarette lighter. It produces a small flame that one could use to light something small. What they used to smoke would be a cigarette. But inside here is a pressurized liquid called butane. When we reduce the pressure inside the container by pressing on this black knob, I'm letting out butane gas, because as the pressure diminishes, it transfers, makes a phase change from the liquid to the gaseous state. And by also igniting a little spark, you can get a flame to start. And as long as there's some butane inside the lighter, then you can feed a flame and you can refill the lighter and so forth. What we've got today are 3 different lighters, and we're going to keep track of them by color. We've got a blue one, an orange one, and a yellow one. And before we do anything else, and before we get it wet, and after you're done playing with it, what we're going to do is set it on a scale to record its mass. And I'm getting 12.65 grams, 12.65 grams for the blue lighter. For the orange lighter, 13.06. And for the yellow, 13.12. I'm going to write those down. One moment. Okay, so I've got the mass of each of the 3 lighters. I've written it down. Now for the ingenious part. We're going to deliberately release the butane from these lighters, not by igniting it. We're simply going to press on the side of the lighter, the black button, in order to release the butane. And as the butane makes that phase change from liquid to gas phase, it should make bubbles. We're going to capture the bubbles in a long, skinny tube. Now, this looks a little bit like a burette tube, which we'll use later in the year, but it's a long, skinny tube that has a closed end at the top and an opened end at the bottom. And what we're going to do is capture a gas in this tube. And there are volume markings all the way down. So at the top, where the closed end is, it says 1 milliliter, and then 2, 3, 4, 5, all the way down to 50. What we're going to do is start by filling this eudiometer tube with water all the way to the top. And even you can overfill it, and that's okay. So I've even got it a little bit overfilled. And what I'm going to do is put my thumb over the tube and invert it into a sink full of water. So if you take a look at this sink, students, I filled the whole sink with water. Then I'm going to take a funnel. This funnel, I'm going to submerge in the sink at the very, very bottom, and I'm going to put the eudiometer tube's opening over the funnel opening. And the reason for the funnel is to help us to direct the bubbles that will be released from our butane lighter into the tube. So it's going to be hard to see this, and in fact, you won't be able to see this, but I've got a tube that's completely filled with water, and under the water I've got a funnel upon which the tube is sitting. Now I'm going to get my hands a little bit wet. I'm going to put the butane lighter under the funnel, and then I'm going to press the black button. And as I do that, if you can look carefully at the tube, there are bubbles rising in the tube. Now, those bubbles aren't air, they're butane, because I'm letting loose the butane from the lighter into the tube. And what I'm going to do is I'm going to release somewhere between, as the directions of the lab say, between 45 and 50 milliliters of butane. And so I'm going to keep bubbling away, bubbling away, bubbling away. And I'm keeping an eye on the volume markings on this eudiometer tube. And I'm going to stop when I get to about 45 milliliters. There we go. I'm going to take an exact reading. So in addition to saying somewhere between 45 and 50 milliliters, I'm going to get an exact reading, reading the curve of the fluid inside the meniscus. And I've got, in this tube, 46.8 milliliters of butane. Now for the rest of the lab, I was using the blue lighter, and I'm going to set the blue lighter aside on a paper towel. I'm going to help it dry a little bit by just wiping any excess water that I can see. And then I'm going to set it aside to dry so that we can weigh it at the end. I'm then going to repeat the procedure with the yellow and the orange lighter. Now, I don't need to actually show you how to do that, but because it's the same thing. But I am going to refill the eudiometer tube with water, just like we had before. I'm going to put my finger over the opening, invert the tube into the sink that is filled with water, and don't forget the funnel, which is in the sink. I'm going to finagle the funnel's opening into the opening of the eudiometer tube, and then let's say I go for the orange lighter next. I would release butane into that lighter, and I would keep going until I've reached 45 milliliters or thereabouts. You would do that for 3 trials, for the blue, for the orange, and for the yellow. And in each case, we're going to let the lighters dry and collect the mass at the very end. So once they're bone dry, we will then take the scale and we'll weigh them again. And then we'll be ready to calculate once we've got those masses. This is the molar mass of a gas calculations section. Here's our data table. We had a blue, orange, and yellow lighter. Their initial masses were 12.65 grams, 13.07, 13.12. After they had dried, their masses were, for the blue lighter, 10.41 grams, 11.02, 10.95 grams. The volume of butane that was collected in that long, skinny eudiometer tube was 46.8 milliliters, 45.2, 48.4 milliliters. Now, 2 other pieces of data that we'll need to complete this lab report. First, I've got here an electronic thermometer barometer combo. And if I hold this close, you might be able to see it. Our temperature today at the very top is 27.5 degrees Celsius. And that's the same for all 3 trials. You can presume that the temperature doesn't significantly change. The other important number that we need from this electronic thermometer barometer is 29.09 inches of mercury. Now that's a pressure unit, but since this is an American instrument, they read things in inches, we've got to convert out of that. So 29.09 inches of mercury for the pressure, 27.5 for the temperature, degrees Celsius. And that can be the same for all 3 trials. Okay, now let's turn to our calculations. What I'm going to do, students, is work through the calculations for the blue lighter all the way through. And then I'll let you work out the calculations for the orange and yellow. It would be the same steps, but you would use the numbers for, of course, the orange and the yellow. So if you look at the analysis questions, first one, it says, convert the air temperature from Celsius to Kelvin. And to do that, you would add 273. So 27.5 degrees Celsius. If you add 273 to it, you can use a calculator if you want. 300.5. So and the work I would show would be something like this. .5 degrees Kelvin, and I'm just going to write a K for Kelvin. 2, using dimensional analysis, convert barometric pressure from inches of mercury into atmospheres. Show your work. And it gives us 2 conversion factors or equivalent statements for you to make into a conversion factor. So let's start with what we know. Our barometric pressure for this lab was 29.09 inches of mercury. We're going to use 2 conversion factors. So I'm setting this up with 2 big sets of parentheses. The things that we need to cross out are inches in order to get into millimeters. And so if you look at the first equivalent statement, it says 1 inch equals 25.4 millimeters. I'm going to write the inches on the bottom so that the unit inches will cross out when we calculate. And then the other conversion factor will relate millimeters of mercury into atmospheres. And as we know, 1 atmosphere, oops, I'm going to put that on top actually. I want 1 atmosphere on top and 760 millimeters of mercury in the denominator within the conversion factor so that we can cross out. So the mercury crosses out, millimeters crosses out. The unit that's not crossed out is atmospheres. So if we punch this into the old calculator here, I type in 29.09. I'm going to multiply by 25.4, and then I'm going to divide that answer by 760. And I get 0.972 atmospheres. So now we have our pressure stated in atmospheres. Question 3, convert the volume of gas collected for all of the trials into liters. Show your work for each of the trials. So I'm only going to show you work for the blue lighter. You would then do the same thing for the orange and the yellow. If I've got 46.8 milliliters for the volume, and we know that a liter is equivalent to 1,000 milliliters. Again, we're writing a conversion factor showing the unit that you begin with crossing out and the unit that you want at the end. So effectively what you're doing is moving the decimal 3 places to the left. So 0.0468 liters. All right, so far so good. We just did some unit conversions there. Now we're going to add a little bit of a twist. When you collect a gas over water, as we did in this lab, you inadvertently collect water vapor all the time. Whenever you're collecting a gas over water, water vapor is mixed in with the gas that you're collecting. So we intended to collect butane, but we actually collected in that eudiometer tube a mixture of butane and water vapor. Well, we can use Dalton's law to isolate just the portion of the pressure that was butane. In other words, since we know Dalton's law says that in a mixture of gases, the sum of all the individual gas pressures, in this case, the pressure of butane and the pressure of the water vapor, should equal the total pressure. Well, what we found in question 2 was the total pressure. If you look at the table next to question 4, it says, okay, if your air temperature is some number of degrees Celsius, then your water vapor pressure is the number that's listed. So I need you to actually look at the lab report here. Since our air temp was 27.5, you might say, well, should I go with 0.0373 atmospheres or 0.0395? Well, why don't we average the two? Since our temperature was right in between them, let's take the average. So I'm going to add up 0.0373, 0.0395, and divide by 2. I get 0.0384. So I'm going to attribute the water vapor to 0.0384 atmospheres of pressure. And that all equals the total pressure of 0.972. Aha. To get the pressure of butane alone, we'll simply subtract. So we'll take 0.972 minus 0.0383, and we get a butane pressure of 0.9336. Now for the fun part, students. At this point in the game, we've got several pieces of information about the butane that we collected. We've got its temperature from question 1. We've got its volume from question 3. And then using Dalton's law, we've got its pressure that we needed to adjust due to the water vapor from question 4. Question 5 says, okay, let's use the ideal gas law now to calculate the number of moles. So we'll use PV equals nRT, and we'll plug in the information we know. Our P is what you got for question 4. Your V is what you got in question, I think it was 3.0468 liters. The number of moles is what we're solving for. The universal gas constant R is always 0.08206 liters atmospheres over moles times degrees Kelvin. And then lastly, the temperature stated in Kelvin was 300.5. Yikes, that's a lot, isn't it? A lot of stuff. Well, let's pull out our calculator. We're going to solve for N. So to finagle this in my calculator, I'm typing 0.9336 times 0.0486. I'll divide that answer by the universal gas constant, 0.08206. And then I'll divide that answer by 300.5. I get a value of N that's quite small, and that's okay. 0.00184 moles of butane. According to our data, we got 0.00184 moles of butane collected in the eudiometer tube. Okay, now for some actually very straightforward, exciting stuff. In question 6, it says, refer back to your data table, subtract the initial mass of your lighter minus the final mass of the lighter. Okay, for our blue lighter, it was 12.65 grams initial mass, 10.41 grams final mass. So if we just subtract those out, 2.24 grams of butane. Question 7. So in other words, the difference between the initial and final mass is equal to the number of grams of butane that you released and then captured in the eudiometer tube. 7, calculate the molar mass of butane by taking your mass divided by your number of moles. Well, we've got our mass in question 6. You've got your number of moles from question 5 from the ideal gas law. So let's divide 2.24 grams divided by 0.00184 moles, grams per mole is the molar mass. Let's see what we come up with here. Huh. 1,117 grams per mole. Yikes. Yikes. Find the average of the 3 molar masses you just calculated. Show your work. So in question 8, you would then say, okay, you'll have a molar mass in question 7 for the blue lighter, for the orange lighter, for the yellow lighter. Question 8 says, take the average of the 3. So average the 3 molar masses you have calculated. Remember, I'm only showing work for the blue lighter here. Question 9. The actual formula of butane is C4H10. Use the atomic weights from the periodic table to calculate the molar mass. Well, students, if we look up on the periodic table, the atomic weight of carbon, you'd get 12. So 4 atoms times 12 gives you 48. And then for hydrogen, we have 10 atoms. Its atomic weight rounded to the 10th place would be 1.0. So 10 times 1.0 is 10.0. Students, our expected molar mass based on the periodic table is 58 grams per mole. How does that compare to what you found when you averaged all 3 molar masses? Well, I can tell you that for the blue lighter, our atomic weight is way higher than 1,217 is much, much bigger than 58. That's okay. All right. We get all kinds of funky data in class. And remember, I'm much more interested in your ability to calculate and analyze the data than in getting so-called quote unquote right or correct data. There is no such thing as correct data. Data is just information that we can use to make interpretations. Well, let's make some interpretations. Calculate your percent error. Use your answer to question 9 as the accepted value. Use your answer to question 8 as the observed value. Okay, well, we'll get a pretty darn big percent error here. Let's assume for the sake of our calculation that I just needed to use the blue lighter. So I'm going to say that for question 10, my accepted value. So if you remember, percent error is observed value minus accepted value, all in absolute value brackets, over the accepted value. And then to make it a percentage, multiply by 100%. Now, you might get a percent that's much above 100, and that's okay. I think that's what we'll get here. If I'm using my blue lighter as if it were the average for all 3 of the lighters, I don't know how that'll work out, but if it were, you would do something like this: 1,217 minus the accepted value of 58, all over 58. And then we would convert it into a percent by multiplying by 100. So I'm getting 1,998%. Okay, it's a big percentage. That's okay. Huge percentage. Question 11. This is probably the most interesting one. What if one of the following scenarios happen? What if some bubbles of butane escape from the lighter and don't actually make their way into the eudiometer tube? What if they maybe got off the edge of the funnel and didn't bubble in? Okay, how would your experimentally determined molar mass be affected? And your choices are either artificially high, or artificially low? There is a right answer. I want you to think about that. B, if an air bubble is left in the eudiometer tube before the gas is collected, like when you were flipping that eudiometer tube over so that it was in the sink, the mouth of the tube was in the sink, if you mistakenly moved your thumb off that tube or forgot to cover it in the first place, you would have gotten a big air bubble in the eudiometer tube, and you would then have attributed air as if it were butane, which is incorrect. Would your calculated molar mass be artificially high or low? Explain or think about it, and then circle one. Question C, if a student forgets to adjust the total pressure to calculate the pressure of just the butane. In other words, they forgot to do question 4, where we use Dalton's law to account for the pressure of the water vapor. What if they had forgotten that? And they instead said, well, the total pressure is all butane. Would your calculated molar mass be artificially high or artificially low? Think about it and circle one. Thanks for your attention. Good luck on the report.